Let's take a look at our first module lecture here, Engineering Properties of Soils, for our course on concrete and asphalt materials. The topics we're going to cover with this module lecture are the basic types of soils, the field test to identify silts and clays, mass volume relationships, soil classification test and sieving, plasticity of the soils, soil classifications. We're going to look at soil water, soil strength and settlement. Of course, we're going to take a look at some test procedures. And of course, the Atterberg limits test. Why is it important to understand the engineering properties of soils? Well, it's important to understand the underlying characteristics of the subsurface soil condition layers for structural foundation design parameters. We want to know how these soils are going to be able to support the structure we're going to load these same soils with. It's also important to understand these properties when designing the components used in the construction materials for the subbases and embankments for roadway surfaces, along with the requirements for earth dams and other earth grading projects. So again, we want to know what the soils are going to do in order to support the structure we're going to load it with. So we have some basic types of soils. Classifying soils into groups with similar consistencies can provide engineers and design professionals with general guidance procedures about the engineering properties of the soils through the accumulated understanding of the soil particles and sizes, or particle sizes and shapes that we have of this subsurface soil material. Soils within the engineering fields refers to soils that are unconsolidated materials within the subsurface area of the Earth's crust. This also refers to all soil materials above the bedrock surface that make up both the mineral, of course silt and clay, and the organic materials found in topsoils. And of course, organic materials are those materials that have been on the surface and they decay, and we know them as a topsoil material. Along with these components, soil materials also contain air and water that balance out their volume and weight characteristics. Mineral soil particles are the result of both physical and chemical weathering that take place over time and, of course, centuries. Physical weathering comes in the forms of water, frost, wind, to name a few, while chemical weathering is the result of water flowing through the rocks and leaches out mineral components of this rock material. The soil particles that are formed in this manner are known as clays. So let's take a look at some granular and cohesive soil types. And we have an image here or a picture off to the right. And the differences in engineering properties results from the large variations in the soil particles and shapes of the grains that are collected from a soil sample. So basically, as we excavate material, dig material, we're going to have different grain sizes that make up that soil area or the sample that we collect. So if we look at gravel and sand soils, of course, at the top picture, we have some gravel material. We can see the particles are larger, more rugged. We take a look at the bottom image, of course, the sand soils, finer materials, and so on. So gravels and sands are rounded or cubical grains that are supported by adjacent grain structures. These soil types can carry significant loads based on their soil configurations. So again, these soil particles, when they're tightly bound together, Mother Nature took its course, rain, pressure on it, allowed these particles to move back together. So it gives us a lot of strength bearing capacity. This is due to the weight of the load being transferred amongst all the grain particles through friction movement. So again, these particles, as we're loading them, it's distributing that load across all the grain particles due to the way that they've moved into their the void areas to eliminate those areas and to make it more compactable or compacted. Gravels and sands are Fairly easy to compact, which helps to improve the load carrying capacity of the subsurface soil layer conditions. So again, as we use water and we use compaction equipment, we're able to get those grains and particles to move back together. So it gives it a nice bearing capacity which will carry loads. This is what makes gravels and sands an excellent soil material for construction purposes. Let's now take a look at cohesive soil types. And again, we see our upper image here, our picture gives us that. And it's a clay type material. And our lower image shows a clay material that's been saturated with some water. And of course, we can see how it starts to stick together. And the characteristics of that same soil material changes. So cohesive soil means clay or a fine grained soil with a high clay content. Cohesion stands for the force that holds together the molecules or particles together within a given soil sample. It is important to remember that cohesive soils do not crumble, and when they become wet or moist, will become plastic in nature and will form a slick ribbon. And that's what that lower image shows, how that clay has gotten moist and now it becomes like a slick ribbon. With this in mind, cohesive soils are hard to break up when dry and exhibits significant cohesion when submerged as the molecules or particles move closer together. Cohesive soils include clay silt, sandy clay, silty clay, clay, and organic clay. As we continue to look at clay, let's look at clay water holding capacity. Clays are softer soils and do not carry loads well in relationship to gravel and sands. And this is due to the fact that clay will absorb that moisture and water. Clay has a good water holding property and characteristics. Clay shrinks as water evaporates. So now we have to picture that movement of clay. As water comes into the picture, clay will absorb that water. It causes it to expand. As the water starts to evaporate, clay will then lose that. It starts to lose it, and now it starts to compress or shrink. Again, clay expands as water is absorbed. Of course, clay will lose water when a structural load is placed on it, causing the water to be squeezed out of its pores. So now just picture a sponge. We take that sponge, it'll absorb the water. We could look at that sponge, but it doesn't really look like it has any moisture in it or water. Now we put a load on it, put our hand on top of that sponge and push down on it. Now we see all that water coming out. So that is a spongy material. It's going to suck up the water. When it's around us, it's going to let the water go when a load gets put on it. And we have to concern ourselves with that. The strengths of clay are directly related to the surface charges that forces grains to form together in an edge to side pattern due to the simple fact that the opposite charges attract. Clay soils are based on a fluctuant structure that has voids between the soil particles, while granular soils have a denser configuration as soil particles are closer together with limited void spaces. Granular soil characteristics: larger grain sizes than clays. We have particles tend to be more or less spheres or cubes. Bound water is small compared to the overall mass. Silt particles may not be visible to the eye, but tend to be gritty, have dull appearances, and lack cohesion when dry. Our clay soil characteristics, on the other hand, have small flat surfaces, negative positive surface charges. We get bound water on the surface. Different clay minerals are different in size. Swelling clays absorb water into a crystal lattice. Shrinkage due to evaporation or loading, so again a big concern with clay. Let's take a look at the organic soil characteristics. Of course, they tend to be fibrous and or amorphous. They're brown to dark in color, high moisture holding capacity or content. Water may run out when squeezed. Dried organic soils may combustible or be combustible. Let's take a look at silt soil characteristics. One of the things we have to remember is silts are coarser than clays and not bound tightly together. We also have to remember that silts are gritty and less plastic and dull when cut than clays. With the dry strength test, silt grains appear to lose their apparent cohesion and the sample powders easily over time. In the shaking test, a saturated silt sample will become more denser when jarred, and water will tend to seep to the surface of the container. So we get a separation there. And of course, this phenomenon is known as dilatancy within the soils engineering environment. Let's take a look at the factors that are related to the mass volume relationships of soils. Soils are made up of a combination of dissimilar materials that fall under the categories of solids, liquids, and gas. And of course, our liquid is water and our gas is air. The overall strength and behavior considerations of our subsurface soil conditions is a function of the interaction that takes place between these three components based on the percentages of their volume distribution. These overall component percentages will play a role within the design parameters that must be considered when designing our supporting structure or subsurface for our highway or roadway system. In order to develop our weight-volume relationships, we must separate the three phases into their individual components. And here's what we're looking at. So the soil component separation, as we move left to right, of course we get the ideal case. There's no voids. There's no air to no water. We have just soil solids, nice compaction. We're going to be able to hold a lot of load on it. Our dry soil, we're going to have air and the soil solids. Of course, we have a saturated situation, water, soil, solids. And of course, our partially saturated soil has all three components in different percentages, of course, air, water, and soil solids. And as we look at these relationships, it's important that we get an understanding through our soil phase block diagram. So of course we look at the volume and the weight off to the left here, but now we have what are our percentages in volumes. So we have our air, our water, and our solids. And what's the weight of our water and solids? Let's take a look at some things to remember with the mass volume calculations. The density is given or is assumed to be the total unit volume of 1 cubic centimeter or 1 cubic meter. Water content is given along with the total density or the total mass. The void ratio is given and the relative density is assumed a unit volume of the soil solids. That's going to equal 1 cubic meter. Field soil conditions referred to as loose or dense. Density index is the soil's density relative to the maximum and minimum for that type of soil. Assessing the stability of the granular soils is known as the relative density. Let's take a look at soil classification test and sieving. The two most important types of tests used in classifying soils are grain sizes and plasticity for grain types. Soils are often heterogeneous, composition and properties that vary with the location. Soils are often anisotropic, properties that vary with direction. Soils are a particulate medium made of particles that are not held together. Of course, load transfer mechanisms are complex. Soils are generally assumed as continuous median or media for simplicity. Soils almost always fail in shear. Grains slide over each other on the failure surface. Stress grain diagrams of soils are similar to those of strain hardening and softening materials. Soils are generally assumed to be linear, elastic, at loads much lower than the failure load. And here we have some examples of our classification tests that we would be looking at. We have the sieve analysis is the larger particles like grains and sands, and that's off to the left here just below, as our sieving trays here or canisters. The hydrometer test for finer particles like silt and clays. Let's take a look at the hydrometer analysis. With the hydrometer, readings are taken at various times, and the soil percent finer than a given diameter D can be calculated and a grain size distribution plotted. The sieve and hydrometer techniques may be combined for a soil having both coarse-grained and fine-grained soil constituents. Grain size distribution. Sizes of the grains vary greatly in any soil mass. To classify a soil property, you must know its grain size distribution. Grain size distribution for coarse-grained soils is determined through the sieve analysis procedures. Grain size distribution for the fine-grained soils is conducted by the hydrometer analysis. Another technique to identify soils is through the soil color. And a Munsell color chart is used for this procedure. We identify the soils through the color through the different subsurface layers. So this color or soil color chart allows engineers and construction managers to uniformly describe the soil color based on the distribution of the soil layers in the subsurface soil conditions. In the field, engineers and construction managers can compare the colors found in the soil with the color chips found on the chart for soil classifications. So again, we take our color chart, we have a excavated area, a trench, and we can get in there and we can start to look at the soil distribution and the colors that we have and start to classify them in that manner. Let's take a look at the sieve analysis test. This is conducted by taking a measured amount of dry, well pulverized soil and passing it through a stack of progressively finer sieves with a pan at the bottom. The amount of soil retained on each sieve is measured and the cumulative percentages of the soil passing through each is determined and is referred to as percent finer. And here is basically a illustrated example of how the sieve analysis works. We start at the top, we put our soils in, and as each one is trapped, the mesh material is finer and finer and finer, and of course we get down, so we get our gravels, our sands, and our fines. Of course, here's some different size sieve trays or canisters. As we can see, the mesh material is different on each one of these. If we look at how this is determined, the smaller sieve designation. So the smaller sieves are numbered according to the number of openings per inch. So we have, in this particular case, 1 inch. We count the openings. And of course, there's 10 openings per inch here. And this would give me a number 10 sieve. Of course, the sieve numbers and the millimeter opening sizes that we have. So we have the sieve number, and then we have the opening size that is reflected or in relationship to that sieve number. Again, collection here, as we can see, we have, if we move right to left, we have the coarser materials and coarser, and we keep getting those fine materials as we collect them. And then we would take each canister as we take it apart, we would weigh it, get its mass or its weight, and then figure out what our grain distribution is on that particular soil sample. So now that we've collected the information through our sieve analysis test and we've weighed everything out, we can do a grain size distribution. So we have our percent finers on the y-axis. Along the upper x-axis, we have the sieve designation. Of course, the lower, we have the grain size. And we can plot this information. So we're looking at plotting our grain. And as we can see, the percent finers here are 81. We have a number 20 here, sieve size. So we plot all that good information. And of course, our curve that connects all our points together. Unified Soil Classification System, or the USCS, Atterberg limits based on laboratory testing. Of course, we're looking at ASTM D2487. We have a plastic limit, or the PL, the water content at which the soil starts to exhibit plastic behavior. The liquid limit, LL, water content at which soil starts to exhibit the liquid behavior. And our plasticity index, or the PI, is a numeric difference between the LL and the PL measure of plasticity. Of course, clays have a high PI, silts have a low PI. And if we look at the classification group symbols, of course, our main soil type is going to be gravel, sand, silt, clay, and so on. Our symbols, of course, gravel is G, sand is S. Now we get into a situation, silt would have the same starting letter. We got to call it something else. In this particular case, M. Clay would be C. And then we start to look at our different groups here, the subgroup. What do we have? Is it well graded, poorly graded, silty, clay? And then we get some more letter designations. And our classification group symbols, in this particular case, if we had a gravel, well graded, of course, our classification is going to be a GW. If I get down in here to silt, and our symbol for silt is M, of course, and we have a liquid limit that's less than 50%. So in this particular case, now we have a ML as our classification group symbol. And of course, again, if we look at other things, we just mentioned it, gravel and the letter designations that we have. Let's take a look at a plasticity chart. So the A line generally separates the more clay-like materials from silty materials and the organics from the inorganics. The U line indicates the upper bound for the general soil conditions that we have. And it's very important to note that if the measured limits of the soils are on the left of the U line, they should be rechecked. So if we look at our chart here, we've got the liquid limit on the bottom, we've got our plasticity index on the left-hand y-axis, plasticity range along the top, and of course our shrinkage potential on the right-hand y-axis. And as we can see, we're moving from low, medium, high, and very high on that shrinkage possibility or potential with the soils that we have. So again, we plot this information, or we look at our plasticity chart, and we want to make sure that if anything moves to the left of that U line, we want to recheck it. Our unified, again, soil classification system, as we can see, grain or coarse grain soil classifications and grading. We get well graded, poorly sorted, and we get poorly graded, well sorted. So that's what we're looking to do here with our grain distributions, trying to determine, do we have well graded, poorly graded, and so on. So when we go to design our structure, we want to know, again, what that soil supporting characteristics are. If we continue to look at the unified soil classification system, of course, we're looking at the coarse grain soil classification, and we want to get somewhere between 5 and 15% fines. And the ideal thing is 10%. So the dual symbol, two symbols separated by a hyphen, in this case, we're going to look at SP-SC, are poorly graded sand with some clay materials in it. So the first symbol, the SP, identifies sand or gravel and the grading. The second symbol, the SC, identifies the type of fines. Do we have silt or clay? Hydraulic conductivity significance, fines lower than K by reducing effective porosity, plus other soil properties or characteristics that we would have. Let's move along here and look at the American Association of State Highway and Transportation Officials classification methods. And this is also known as AASHTO. And the American Association of State Highway and Transportation Officials use 7 basic soil groups designated A1 through A7. The soil is placed into groups by performance characteristics. A1, of course, is the best. A7 is the worst. A1 to A3 are sands and gravels. A4 to A7 are silts and clays. Of course, there is an A8 designation, which is reserved for unusable peat, of course, organic materials. The following are 2 charts and tables that you can use to find the designated soil group. And of course, this will be in the text material, or you can view this with the PowerPoint presentations. The USDA soil classification system uses a triangular shape with soils designated or placed on the triangle to give you an idea of how to go about looking for the makeup of the soil content. And if we look at the triangle or the texture triangle, 12 soil classes defined by the percent sand, silt, and clay that we have. Silty clay is 40 to 60% clay, 40 to 60% silt, and roughly 0 to 20% sand. Lab analysis or field or texture by feel analysis can be conducted. Gravels are not included. Using a modifier, the percentage of sand, silt, clay normalized to 100% without the gravel. So again, we can see this triangle here. We have clay, silty clay, sandy, clay loam, and so on. And basically how we use this triangle is we look at the soil ribbon strength, estimates the percent of clay that we have. And if we get the gritty to smooth, the grittiness estimates the percent of sand versus the percent silt that we have. So how do we use the soil texture chart? We look again, it's the sand plus the silt plus the clay equals 100%. The texture, in this particular case, once we look at it, it's going to be loam. So I have 40% sand, I have 40% silt, I have 20% clay. So I move across, I say, okay, what's my percent clay? I've got 20%, I move across. It's in the loam area. Now I say, well, how much silt do I have? I have 40%. Let me move down. And of course, how much sand do I have? 40%. And that puts me right into the loam area. Let's take a look at another example of using the texture triangle that we have. In this particular case, we got 20% sand, 20% silt. Of course, this means we have 60% clay, 100%. Again, I add it up. In this particular time, or this case, we're going to have a texture that's going to equal clay. So again, 60% clay, I move across, 20% silt, 20% sand, and it puts me right into the clay area. Let's take a look at the soil water factor that we have to consider, the types of water found in soil. So we get free water or gravitational, and it's found below the water table and also free to flow under the forces of gravity. Capillary water brought up through the soil pores due to surface tension and found above the water table in certain soil conditions. Attached water or held water, moisture film around soil grains. Quantity may be very large for clays. Surface tension in soil water. When soil is saturated above the groundwater table, it is difficult to establish groundwater table. Apparent cohesion in sands and silts will mistakenly indicate a clay material might be present. We get frost heaving, water in large pores freeze, water in smaller pores not frozen, drawn to the ice crystal freezes, enlarging the ice crystal. Capillary water moves up pores or spaces to replace these small water particles. And this is a continuous process and a big problem that we have to concern ourselves with when we do designs in order to eliminate or try to reduce as much frost heaving as possible. This concludes this Module 1 lecture on the engineering properties of soils. Please make sure you look at the text materials and the PowerPoint presentations to obtain more information on the topic of engineering properties of soils.